So good evening, everyone. So let us continue our discussion. Uh, so we have completed 3 weeks, three classes. So let us today start the fourth class. So this class we will be basically trying to we'll basically try to understand the collapse limit state collapse in shear. Okay, so we will try to see how to design uh, beam section. Okay, under the under the criterias. Okay, so that it resists the shear. Okay, so it has the capability of resisting shear. So last classes we basically designed for the flexure, like the bending, right? So here we will be going through one more limit state of collapse, which is shear. Okay, so we had most mainly four. Okay, flexure, shear, torsion, and axial tension compression. So these are the four. So we the most important is the bending flexure, but other than that also these are also like very crucial. Okay, so basically these four limit states for strength, and for serviceability there is deflection and cracking, which will be going through in the coming classes. Okay, so let us start the design for shear. So basically if you see here, so this is a singly reinforced beam, okay, having some UDL, that is uniformly distributed load. So here the longitudinal reinforcement, it is basically resisting the flexure as we just discussed, the bending. But if there is some definitely with the bending there will be some shear component also. Okay, but that is not equipped, like the rebar is not completely equipped to resist that shear component. Okay, so it may or may not be, there is no guarantee. Okay, so that's why it is very important that you know it is important to see and check whether the design is capable of resisting shear. Okay, otherwise there will be chances of failure due to sliding. Okay, sliding of sections. Okay, so shear is basically nothing but sliding. Okay, failure due to sliding failure basically. So if you see here, say for example this is a section. Okay, so here if you see, these are the shear stresses acting at the surface. So if you see in the diagonal, okay, so in the diagonal there can be two types of stresses that can act. Okay, one is tension, okay, and one is compression. Okay, so that is basically dependent on the location of the diagonal. Okay, so in this case if you see, the location of the diagonal is somewhat in opposite direction. Okay, in opposite direction as compared to the stress. Okay, the shear stress. So it is trying to, it is trying to uh, exert some tensile force. Okay, so it is trying to elongate. Okay, so that's why it is called diagonal tension. But when the diagonal and the shear stress component is in the same direction, okay, so then if you can see, what happens is it is trying to compress the diagonal, right, diagonal component. So that is why it is called diagonal compression. Okay, so it is not allowing it to move like this, instead it is acting the opposite. Okay, so that is what diagonal tension and diagonal compression is about. So if you see here, this is the tension which is occurring in beams. Okay, so with that concept if you see, so here it will try to extend. Okay, so the slice will try to elongate, so that's why literally, so that is why it is tension in beams. Okay, similarly if you see here, there is shear failure, this is shear tension. Okay, so when the shear failure is occurring near the supports, okay, so it is always in shear tension. Okay, so and this angle is generally about 45 degree. Okay, so that is near to the supports. Okay, similarly, if the shear is occurring in the middle of the beam, okay, simply supported beam. If it is occurring in the middle, or any beam, any type of beam, so if it is occurring in the middle, so then the flexure type of shear is occurring. Okay, bending shear is occurring. So the cracks that will occur will be bending. Okay, bending cracks, flexural cracks. Here it will be shear cracks. Okay, so these cracks are basically 45 degree, whereas these cracks are basically 90 degree. Okay, if you can see here, it is 90 degree, right? So Apart from that, if you see here, when the cracks passes through the reinforcement, right, so there will be some type of bonding. Okay, so some strength will be there which will resist this propagation of crack. So as you can see, this crack has moved up till the rebar, but it is not passing after that, so because of the shear bond. Okay, so there is some shear strength provided by the rebars. Okay, so longitudinal rebars is providing some shear strength, because of which it is not able to propagate through it. However, it is not fully capable of resisting the shear. Okay, 100%. So that's why we need another component of some steel reinforcement, which are known as stirrups. Okay, so we will study now. So that's why the longitudinal reinforcement, although it is capable of resisting the shear crack because of the bond, shear bond, however, it is not fully 100% capable. Okay, so it will be partially only able to resist, right? So apart from that, there is this shear compression. Okay, so the slice. Okay, so it is compressing the inner portion. Okay, so that is shear compression. So if you see here what I was talking about, it is this. Okay, so apart from the longitudinal reinforcement, we need to add some vertical reinforcements. Okay, so these vertical reinforcements are nothing but the stirrups. Okay, so this is this can also be said to be lateral reinforcement. Okay, so this is longitudinal reinforcement because it is going through the axis of the member, right, the beam. Okay, right. But in this case, the stirrups, it will be generally vertical. Okay, vertical or inclined. Basically we keep vertical, so this is vertical stirrups, say for example. And if you give some if you place the stirrups at some angle, it will be inclined stirrups. Okay, so this is basically nothing but lateral reinforcement. In case of beam, we call it stirrups. In case of column, we will call it tie beam. Okay, tie beam or tie bars. Okay, so this is the thing. So stirrups is basically for beam, and tie bars are basically for this one, columns. Okay, so but the this is same, the function is same, so it is basically for resisting the shear. Okay, so here if you see how to describe the stirrups, so basically we give the diameter of the rebars, which will be generally lesser than the longitudinal bars. Okay, so it will be around 8 bars, 10 bars, something like that. Most uses the 8 bars. Okay, and secondly we give the number of legs it has. Okay, so legs is nothing but this extended portions. Okay, so if you can see here, there are two extended portions, so it will be two leg. Okay, if there is some extra, say for example, apart from these two, there is some one more bending here, more extension here. Okay, so more extension or protrusion is here, so we will give it three. Okay, so it will be three legs then. Okay, so if instead of one there are two more, one, two, three, 1, 2, 3, 4. Okay, so then it will be four legs. Okay, so like this. So basically the extension is called the legs. Okay, so here generally we give two legs. Okay, so it is like the bars will start from here, then it will be bended here 45 degree, then it will be bended 90 degree, 90 again, 90 degree, again 90 degree, and lastly it will be but again 45 degree, right? So like it is started from here, then it will be bended like this, like this, like this, like this, and then again it is ended here. So like this, it is called two legs. Okay, so this is the 8 diameter rebar, and the legs are 2. Okay, and third component which we use for detailing the stirrup, describing the stirrup, is the center to center distance of the stirrup. So stirrups is will not be one or two. Okay, it will be placed like this vertically, right? So between two consecutive stirrups, what is the distance center to center? So that is the this distance. So these three components are used for describing the stirrups. Okay, defining the stirrup. First is the diameter, second is the number of legs, and third is the distance between two stirrups. Okay, so this is the way we describe a stirrup. Okay, so as I told you, here there are two extensions, so it is two legged. Okay, in this case you can see one, two, and one more extension here. Okay, so that is why it is three legs. Okay, so more is the number of legs, more will be the area of shear reinforcement. Okay, so for two legs it will be 2 into pi by 4 into 5 square, where 5 is the diameter of the stirrup, and for three legs it will be 3 into pi by 4 into 5 square. Okay, and SV will be the spacing of the stirrups. Okay, so as I told you, the consecutive distance center to center between two stirrups will be the spacing of stirrups, and it will be denoted by SV. Okay, so if you see the shear stress distribution in RCC beams. Okay, so if you see, it will basically the if you see here, in the elastic stage, okay, the shear stress distribution will be little bit like mostly be parabolic. Okay, so you can see it is parabolic, not a straight line. However, at the case of ultimate stage, it will be a linear, okay, linear distribution. So it will be something like this, and it will be again going like this. Okay, so I think you have gone through this in this one, the strength of material class or solid mechanics class. So how is the distribution of shear? How is the distribution of bending? So bending is something like this, right? And shear is something like this. Okay. So that is mostly for the this case, the elastic stage. Okay. In linear ultimate stage, it will be linear. Okay. So as you can see from the diagram, the maximum shear occurs at the this one, the neutral axis. Okay, the center. Okay, which is contrary opposite to the bending stress. If you see bending stress at neutral axis, it will be zero. Okay, it will be maximum at the tension and compression zones. Okay, the higher the tension and compression, more will be the bending stress. However, in the case of shear, it is opposite. Okay, shear at these 2 points, there will be zero. Okay, almost zero, because there will be no this one. There will be no sliding, right? So in this case, there will be no sliding. But when you go, inside this one, like more the depth you go, so it will be having the sliding slices will, there will be sliding between two sections. Okay, so that's why it will start to increase. Okay, so that is for a like idealist structure. Okay, but because there is reinforcement and all, so some shear stress is also present here, because it is in the downward portion, right? So the stress will come from here. Okay, so at this point there will be no section to slides, but as we go deep down, so it will be having slides, right? So that way it is like this. Okay, but generally if you take a normal case, okay, so it will be generally like this. Okay, in the middle it is the maximum, and then again it starts decreasing. Okay, so the nominal shear stress, as there is a this nominal basically signifies the minimum shear stress. Okay, so the minimum stress which is required for the design. Okay, so this either we either we get in the question itself. Okay, or we have to find out. Okay, so this is the minimum shear reinforcement that is required for the minimum shear stress, that is the nominal. Okay, so as per clause 40.1 IS 456 2000, the nominal shear stress in beams of uniform depth shall be obtained by tau v equal to Vu by Vd. Okay, so tau v is the nominal shear stress. Okay, so if in the question the value of Vu is given, okay, so that is the shear load, okay, shear design load given. So then you can find the nominal shear stress just by dividing the width and dividing the shear stress, design shear stress, by the width and the depth. Okay, so tau v will become Vu by Bd. So Vu will be the shear force due to the design loads. B will be the breadth of the member, which for flange section shall be taken as the breadth of the web. Okay, and D will be the effective depth, which we discussed in the starting classes. So if you see this section, for example, so there are three types of bars. Okay, bars. So number one is the bent up bar. So bent up bar is like this bar is mainly used for sections which undergo cyclic loading. Okay, so as for example, like if it is a normal case, like load is coming from top. Okay, so then this portion will be in the tension zone, right? So that's why the reinforcement is downside. But if the, say for example, due to cyclic loading, the load is coming from this side. Okay, this side, so then the compression side will be this and tension side will be this, right? So at that time, what we will require is, we will require reinforcements in this region. Okay, so apart from giving the doubly reinforcement, we can also provide bent up bars. Okay, so bent up bars. So also, for example, in the case of moving load. Okay, so moving load, so say for example, in this region, this will be the range for tension. This portion will behave as tension, in tension. However, in this region, this portion will behave in tension. Okay, so then you can give the bent up bar. This one you can give distribution of bent up bars. Okay, so you can place the bent up bars so that the portions which have tension, okay, which acted in tension, have the necessary reinforcements. Okay, so that is the use of the bent up tension bar. Okay, so it will take tension at those places. Okay, apart from the doubly reinforcement, you can also provide bent up rebars to provide tensile reinforcements at the required portions. Okay, apart from that, this which we were talking now, we are talking now, this is the vertical stirrups. Okay, so these are the stirrups which we will be mostly dealing with, the vertical ones. Okay, and it is called stirrup because it is in the beam case. Okay, in the case of column, it will be called as tie beam. Okay, the same thing. And this which I also told you, if it is, those stirrups are present at an inclined position. Okay, at an angle to the, say, horizontal line, so then those are called as the inclined bars. Okay, so here there is a system of bent up bars, stirrups, and the inclined bars, inclined stirrups. Okay, vertical and inclined stirrups. So this is a complex reinforcement section. Okay, so then the shear forces are resisted by combined action of concrete and shear steel. So basically, as I told you, the shear force, okay, yeah, the shear force due to the design loads. Okay, so that will be taken by both the concrete and steel. Okay, but those concrete and steel are not capable of fully taking the shear forces always. Okay, so then there is the requirement of the shear steel, which is nothing but the stirrups. Okay, so stirrups are required so that the required shear strength of the design is met. Okay, because always concrete and the longitudinal steel will not be able to take the shear forces for the design loads. Okay, so if you see in the case of concrete, okay, the shear resistance is mainly present due to the three factors. Okay, and it's a combined effect. So first factor is the shear carried by the uncracked section. Okay, so which will be the 20 to 40% of total shear in compression. Second will be the shear carried by the aggregate interlocking, okay, across the diagonal crack, which will be 33 to 50%. Sorry, and third will be the shear carried by the dowel action. Okay, so dowel action is basically the, like, when the bond thing. Okay, the bond strength. Okay, so when the shear bond, basically the shear bond, when the cracks will go through the longitudinal tension. Okay, so it will try to resist. Okay, so that is nothing but the dowel action, as we just discussed. So that will basically be the shear bond. Okay, between the reinforcement and the cracks. So using this tree, so that will be about 15 to 25%, right? So maximum will be taken by the aggregate interlocking in case of concrete. Second will be taken by the shear carried by the uncracked section, and third will be the this one by the dowel action of the tensile longitudinal tension. Okay, so these are the main three factors through which, using combination of these three factors, the concrete takes the shear resistance. Okay, so as you can see here, these three are present. So this is the aggregate interlocking, this is the uncracked section, and this is the dowel action. Okay, so shear carried by concrete, VC, is a summation of all three. Okay, so uh, after finding this, okay, so the shear carried by concrete, so just subtracting the this with the actual design load shear, we will get the amount of shear that is required by that will need to be carried by the steel or the shear steel. Okay, the shear steel and the stirrups, or the stirrups. So summation of this and this, okay, will take care of this, right? So this will not be only capable of completely taking this load. So therefore, we are, for the remaining requirement, we have to add this BS. Okay, so the shear strength carried by the steel and stirrups, shear steel basically, which is the stirrups. Okay, so as per table 19 IS 456 2000, the design shear strength of concrete, okay, so tau c value, so that is a basically factor of the amount of longitudinal steel present. Okay, so that is 100 AST by BD, or the PT value. Okay, so P value is nothing but AST by BD into 100. So it is a function of that. Okay, so that will give the design shear strength of concrete. So that means that it is the concrete design shear strength is a function of both the grade of concrete as well as the this value, PT value. Okay, so both is taken into account, and based on that the tau c value is determined. Okay, so as you can see here, this is a table. It is taken from table 19 of IS 456 2000. Okay, so similarly, the maximum shear stress. Okay, so maximum shear stress in the beam, that you know, that can be possible. Okay, even after given design, even after providing stirrups and everything. So this is the tau c max value. Okay, so this is the maximum possible reinforcement, maximum possible shear stress a RCC beam can give. Okay, so these are the values for the different grades of concrete. So even like for example, even after providing stirrups and everything, still if the value of this tau v, okay, that is the design stress, okay, so that is greater than tau c max. Okay, so we have to we have to cancel the design. Okay, we have to cancel the design and redesign basically. Okay, so it should never be tau v value should never be greater than tau c max. Okay, it should always be less than tau c max. Okay, so we will be solving some problems and we will then properly understand how it is playing a role. Okay, so that is the this thing. Okay, tau v. Okay, so that is equal to vu by bd, where vu is the shear force as per the design loads. Okay, when you divide by width into depth, effective depth, you get the design shear stress. Okay, so that is the this one, and this value should always be less than this tau c max. Okay, otherwise we need to redesign the section. Okay, so yes, for the shear reinforcement, that is the stirrups. Okay, what should be the maximum spacing? Okay, so as per clause 26.5.1.5 IS 456 2000, the maximum spacing should not exceed 0.75 d for vertical stirrups. Okay, where d is the effective depth, and it should not exceed d for inclined stirrups at 45 degree. Okay, so d is the effective depth. Okay, so vertical it should not exceed 0.75 d, and incline it should not exceed d. Okay, and in any case, okay, whatever be the case, it should never exceed 300 mm. Okay, so that means the spacing, okay, so that the spacing which has to be provided, that should be a minimum of the value we calculated, the value found from here, and 300 mm. So out of the three terms, the value we calculated, SV value, the value obtained from here, and the value 300 mm. So out of these three values, whichever is the minimum, we have to take that. Okay, so then only this condition will get satisfied. Okay, so we will also see this when we solve problems. Okay, now let us see how to design for shear. Okay, so how to design the shear stirrups basically for shear, finding for getting the shear capacity, required shear capacity. Okay, so if you see, like we have the stirrups can be provided both vertically and in an inclined way, right? So initially let us take the vertical condition. So if you see here, this is just the representative diagram. So if you see here, these are the say for example, these are the stirrups and these are the cracks. Okay, so this alpha is basically the angle between the stirrups and the horizontal, okay, horizontal line, or here it is the longitudinal reinforcement, basically the horizontal line. And this beta is basically the angle between the crack section and the crack and the horizontal. Okay, so that is the definition of alpha and beta. Okay, so in this case, if you see the number of effective bars in any region n, that is basically given by cot alpha plus cot beta into d minus d prime by sv. Okay, so you can use trigonometry. Okay, so for example, if you draw here a vertical line, okay, so what we will see is you will see that this one, this is d minus d prime, right? So this is a this is a 90-degree triangle, right? Like the Pythagoras thing, right? So in this triangle, right, this is a right triangle, okay, right angle triangle, right? So here if you see, this by this is tan alpha and this by this is cot alpha, right? So this portion will be equal to this value into cot alpha, right? So this value is d minus d prime, so this is this length is equal to d minus d prime into cot alpha. Okay, so this is the thing. And for this portion, so this will be similarly what will be cot beta will be this by this, right? So this value will be equal to cot beta into this, which is d minus d prime for this portion. Okay, so that means this the whole region, okay, the whole region, it will be equal to cot alpha plus cot beta into d minus d prime, right? So this region will be equal to d minus d prime into cot alpha plus d minus d prime into cot beta, right? So that is the total distance. And if you divide that by the spacing, okay, so you will get the number of stirrups, okay, which is acting, right? So just dividing by the spacing of stirrups, you will get the n value, which is the number of effective the stirrup bars, okay, in any region. Okay, so that is how it is calculated. So this is just a representative diagram. Okay, so here in the case of vertical, okay, in the case of vertical, what will happen is this alpha value will become 90 degree, right? So this alpha value will become 90 degree. So this cot alpha will be cot 90, right? So if you see cot 90, what is cot again? Cot is equal to cos by sine, right? So cot 90 will be cos 90 by sine 90. So cos 90 is 0, sine 90 is 1. So it will be 0 by 1, which is 0. Okay, so this term will get cancelled. So it will, what will remain? D minus d prime into cot beta. Okay, and if you take the beta angle to be 45 degree, okay, so if we assume the crack line is inclined at a 45-degree angle, so it will be cot 45. Okay, cot beta will become cot 45. And what is cot beta? Cot 45, cot 45 will be cos 45 by sin 45, right? So cos 45 is 1 by root 2 and sin 45 is also 1 by root 2. So 1 by root 2 by 1 by root 2 is 1, right? So cot beta will become 1. So what it will remain? It will be d minus d prime into 1, which is d minus d prime itself. So it will become d n is equal to d minus d prime by sv. Okay, now because this d prime value is much less as compared to d minus d prime, we can assume that d minus d prime is almost equivalent to d. Okay, so this d minus d prime will be almost equivalent to d. So here, sorry, I have written this wrong. So this will be d minus d prime. So d minus d prime will be equal to d. Okay, so I forgot to write properly, I'm sorry. So assuming d minus d prime is equal to d, okay, because this d prime is almost negligible. Okay, so as compared to this d minus d prime, this d prime is negligible, so we can consider d equivalent to d minus d prime itself. Okay, so replacing d minus d prime with d, what will it become? N is equal to d by sv. Okay, so that is what it is here. Okay, so the number of stirrups cut by a 45-degree crack line, okay, will be equal to d by sv in the case of vertical stirrups. Okay, so I hope you have understood this one, the derivation and explanation. Okay, so now the actual now this thing will be used in the design. Okay, so the total shear resistance of the vertical stirrups, therefore system, therefore across the section will be given by Vs, which is equal to 0.87 Fy ASV. Okay, so that is the 0.87 is the partial safety factor. So 0.87 Fy into ASV will give you the shear resistance for one stirrup. Okay, and if you multiply with the n number of stirrups, which is d by sv, you will get the total shear force, okay, shear resistance for a given section or given distance. Okay, so that is Vs equal to 0.87 Fyasv into d by sv. Okay, similarly, so that is the shear resistance, right? Similarly, shear resistance can also be written as tau v minus tau c into bd. Why? Because we told, like we just mentioned, what is this one? What is the shear resistance? Okay, what is the shear resistance? It is basically the extra shear, the extra shear capacity, okay, which the beams need to be provided apart from the concrete shear capacity, right? As we just discussed now. So how will we find the extra shear resistance required? That will, we just need to subtract the design shear stress required with the shear strength of concrete. Okay, so if you just subtract the tau v minus tau c value, you will get the tau s value, right? So that is the shear strength. Okay, shear strength for the stirrups. Okay, the required shear strength for the stirrups. So that is Vs equal to tau v minus tau c into Pt. So Vs can be written both this like this and like this. Okay, so equating these two, what we get is tau v minus tau c into bd equal to 0.87 fy asv into d by sv implies gamma v tau v minus tau c equal to 0.87 fy asv by bsv, and ultimately asv by sv equal to gamma v tau v minus tau c into d by 0.87 fy. Okay, so this equation, okay, this equation is a important equation for designing of stirrups. Okay, so please write it down properly, and this equation also. Okay, so this equation and this equation, okay, so both will be used in this one, finding the shear resistance. Okay, and if like this is the amount of shear resistance that need to be provided, okay, when the shear resistance is required. Okay, however, in some cases you will come across in the coming slides, what happens is that this tau v minus tau c value, if you see now, this will be 0 or less than, like this value will not be positive. Okay, that means tau v tau v will be lesser than tau c. That means the design shear strength required, okay, is lesser than the shear strength of concrete itself, which means that there is no requirement of shear reinforcement, because the complete shear strength of concrete is capable of taking the complete shear required as per the design. Okay, so tau v will be lesser than tau c. In that case, that vs is not required, but still we need to provide the nominal shear reinforcement, which we discussed few slides ago, right? Nominal thing, yeah, nominal shear stress. So this still we need to provide. Okay, if even if the tau v value is say for example the tau v value is less than the tau c value, still although we don't need to design in this way, but still we have to give the minimum nominal shear design. Okay, so in that case what happens is this gamma v minus gamma c value is taken as 0.4. Okay, this that is given in is code itself. This gamma v minus gamma c values becomes 0.4, and what is the formula given is asb by b into sv. This b comes here, so asv by b into sv should be greater than equal to 0.4 by 0.87 fy. Okay, so that is a third case. So this is one important formula, this is another important formula, and third is asb by b into sv is equal to 0.4 by 0.87 fy. Okay, so that is mainly the nominal. Okay, when the gamma v value is itself less than gamma c also. Okay, so then we don't have to provide any shear, like we have to design for shear resistance, but we need to provide the nominal shear. Okay, which is as per asb by bsv, which is greater than equal to 0.4 by 0.87 fy. Okay, so now let us go through a problem in order to understand it better. Okay, so say for example, if you take this problem. Okay, so if you take this problem, so this is a rectangular beam which is having a width of 300 mm and actual depth of 500 mm. The design shear load is 350 kilonewton, and the tensile reinforcement that can be provided is 525 mm bars. Okay, and concrete is having a grade of M20, steel of Fe415. So design the stirrups for shear. Okay, and you can assume here the clear cover to be 25 millimeter. Okay, so because here the view value is given, okay, so that value is always taken as the nominal value. If it is not given, then we will take it ourselves, we will design ourselves as per the asb by bsv greater than equal to 0.4 by 0.87 fy, that formula. Okay, but since it is given, we have to check first. Okay, so the view value nominal shear stress is 350 kilonewton, so therefore gamma v will be vu by bd. Okay, so vu is 350 into 10 cube, b is 300, and d is effective depth. Okay, so clear cover is 25, phi is 25, so it is 500 minus 25 by 2, which is 462.5 mm. Okay, so you can substitute it here, so we get gamma v value as 2.5225 newton per mm square. Okay, so now let us find out the tau c, tau c value, that is the design strength of concrete. So as we know, this is a function of the grade of concrete and the pt value, the percentage of steel. So we need to initially find the p value. So for that, firstly ast, which is 5 into pi by 4 into 25 square, which is 2455 mm square, and dividing this by 300 into bd value, that is 300 into 462.5, b into d into 100. So then we get it as 1.769%, right? So this is the p value. Okay, so now if you take table 19, okay, so from 19 you will get that for M20 at a 1.75 p value, gamma c value is 0.75, and for 2 p value, gamma c is 0.79. So this 1.76 will be in between 1.75 and 2, right? So through interpolation, okay, so through interpolation you can see that the gamma c value will come as 0.75 plus 0.79 minus 0.75 into 1.769 minus 1.75 divided by 2 minus 1.75, which is 0.25. Okay, so this value comes to be 0.752 megapascal. Okay, and this is the shear strength of concrete, okay, which is 0.752 megapascal. And from table 20 you can also find the maximum allowable shear capacity of shear capacity of a beam section. Okay, so which is for M20 it is 2.8 megapascal. Okay, so now if you see firstly the tau v value, it is 2.5, okay, which is less than 2.8. Okay, so that means this beam, okay, this beam having width of 300 and depth of 500, okay, so that will be capable of taking this shear. Okay, if this value would have been greater than 2.8, say 2.9 or 3 or 3.1, that means although we would have designed, but that is not no, that will not be capable of taking the shear resistance. Okay, so it will definitely fail for shear even if the tau v, even if we design it using the tau s value. Okay, even if we design for stirrups, still the beam will fail for shear. Okay, so that's why it is very important to check the tau v value, which is 2.5, is less than tau c max, which is 2.8, right? So in this case, as it is less, so it is okay. Okay, so now the second is check the tau v and the tau c value. So tau c is 0.752, whereas tau v is 2.5, right? So tau v is definitely greater than tau c. That means the concrete shear strength is not only capable like only, you know, uh, only it is not capable of taking the complete tau v value, because the tau v value is higher than zero point 0.7, right? So it is 2.5, so we need to provide the shear still, that is the stirrups. Okay, so as I told you, we have to now design, say let us design for vertical stirrups. So mostly we will be using vertical stirrups only. So that this is as per clause 40.4. So this formula, okay, which we just discussed, so it is a very important formula. Okay, please write it down. So this formula, okay, so using this formula we will design. Okay, so substituting ASB by SB equal to VUS by 0.87 FYD. Okay, so here the gamma C value is 0.752. Okay, and this, yeah, view is how what view is tau v into bd, right? So yeah, dd gets cancelled, so b into gamma v minus gamma c by 0.87 fy. So b is 300 and tau v is 2.5225 minus 0.752 by 0.87 into 415, right? So asb by sv equal to 1.471. Okay, so ASB, let us assume that we provide two-legged 10 diameter stirrups. So it is always, stirrups is generally 8 and 10 stirrups. Okay, generally. Okay. So if more like it is generally because the longitudinal rebars are having more diameter. Okay, so it is always between 8 to 10 Okay, and say let us assume we have provided two-legged 10 bar stirrups. So ASV value will be 157 squared. Okay, so we have found ASB by SV equal to 1.471, right? So substituting ASV value, we will get SV is equal to ASV by 1.471, which is 157 by 1.471, that is 106 millimeter. Okay, so as per the clause of IS 456 we just discussed, the the spacing of the stirrups should be minimum of three values. Okay, so one is the SV value, which is 106 one is the second is 0.75d in which is equal to 0.75 into 462.5, which is 346.8 Okay, if this is inclined, then it would have been simply d, which should have been 462.5. Okay, and the third is 300 Okay, so it should be a minimum of 106 346.8 and 300 Okay, So minimum is 106 mm, right? So in order to make it round, making a in order to make it a rounded figure, so we can either take as 100 mm or 110 mm. Okay, so lesser we take, it is better, right? So more, lesser is the distance between the stirrups, more will be the shear capacity, right? So we are taking, let us take 100 mm. Okay, so that means by taking 10 mm, so there are three components, right? So by taking 10 mm two-legged stirrups at a spacing of 100 mm center to center. Okay, so we can take into account the excess design shear load. Okay, which is the shear stress. Okay, which is 2.5 minus 0.752. That value can be taken by these stirrups. Okay, so this is the design basically. 10-5 two-legged at the rate 100 mm center to center. Okay, so this is the spacing design. Okay, now let us now go to the incline stirrups. Okay, so we have discussed the vertical stirrups. Okay, so let us now go to the incline stirrups. So it is almost similar. The design philosophy is almost similar. Only the what will change is alpha and beta value. Okay, so in that case, beta value was taken as 45, alpha was taken as 90, right? But here it will not be, this alpha at least will not be 90. Okay, so beta can be 45, but alpha will not be 90. Okay, so therefore the number of effective bars in one region n equal to cot alpha plus cot beta into d minus d prime by sb. Okay, so the maximum shear that can be carried by one bar will be this one, ASB into 0.87 Fy. Here one more term comes, which is sine alpha. Okay, so sine alpha will be what? It will be basically this divided by this. Okay, so like that means the, because it is at an angle. Okay, so vertically if you see, so that will be lesser. Okay, that will be this into the sine alpha basically. Okay, so the strength, the shear strength will be provided at an axial direction, right? So when you take its this one, uh, when you take its what is called projections, okay, at the vertical direction, so it will be uh, this force into sine alpha. Okay, so this force is what, ASB into 0.87 Fy. Okay, and taking its sine alpha value, it will be the vertical. Okay, so that value will be the maximum shear that can be carried by one bar, because we are finding everything vertical, because the shear the shear force will be acting vertically, right? So that's why it's important to find everything vertical. So it will be ASV into 0.87 Fy into sine alpha. Okay. So therefore, that is for one bar, and for n bars, okay, where n is equal to cot alpha plus cot beta into d minus d prime by sb. Here, as you can see, so the shear carried by n bars will be ASV into 0.87 Fy sine alpha into n. Okay, which becomes ASV into 0.87 Fy into sine alpha into cot alpha plus cot beta into d minus d prime by sb. Right. So when beta is equal to 45 degree, okay, so let us assume that this beta value is again 45 degree, that is the cracking is occurring at a incline. Okay, crack line is at 45 degree, and when we assume again that d minus d prime is almost equal to d. Okay, because this d prime is almost negligible. Okay, so if we assume that approximately d minus d prime is about equal to d approximately, so then what happens is vs becomes ASV into 0.87 Fy. Okay, so here what happens is this cot beta. Okay, so cot beta will be what, cot beta will be this one, cos 45 by sin 45, right? Like cot 45, so cos 45 is 1 by root 2, sin 45 1 by root 2, 1 by root 2 by 1 by root 2 is 1. Okay, so 1 into sin alpha will be sin alpha. Okay, and here cot alpha, so cot alpha is cos alpha by sin alpha, so cos alpha by sin alpha into sin alpha, so sin alpha cancel, so it will be cos alpha. Okay, so cos alpha plus sin alpha it becomes, and d minus d prime we have taken as d, so into d. Okay, and sv is sv, so vs is asv into 0.87 Fy into cos alpha plus sin alpha into d by sb. Okay, so this is as per clause 40.4b of IS 456 2000. Okay, so this is given as for inclined stirrups, and for the stirrups, the your for the vertical stirrups, this alpha value will become 90 degree. So cos 90 is 0 and sin 90 is 1. So it will be ASB into 0.87 FYD by SB. Okay, for that is for vertical. Okay, so basically this is the generalized formula you can remember. So that will take into account both the criteria. Okay, so if you see if you try to like analyze a truss, okay, so in this truss if you see here, so you will see that these members, okay, these members are mainly in tension, okay, so sorry, compression, okay, because it is trying to compress these diagonals, okay, so that will be always a like this is a compression member and that will also result in this compression, okay. So that is in this case, okay, but if this diagonal is in this direction, okay, then it will behave in tension, as you can see here, okay. So uh, if this is compression, so this two will behave in compression, but this will always behave in tension because it will try to elongate, okay. So that's why, so there is a variation, okay. So one member will one diagonal or one section will behave in tension, one will in compression. That will be depending on the load and the criteria, okay. So the single or group of so here if we consider a single or group of parallel bars, okay, all bent up at the cross section, okay, so then, okay, so together if you say, so then what will be the value? It will be VUS equal to 0.87 FYASV into sin alpha. So this value, okay. So for one bar, so instead of one bar, also if you take it as a group of parallel bars together, then also it will be 0.87 FYASV into sin alpha. But this ASV value will increase because it is a group of parallel bars, right? So number of bars ASV will also multiply, okay. So that way it will increase, but the formula will remain the same, okay. So now let us consider one more criteria. See, let us say that the beam is not of equal uniform depth. Okay, so one portion it is different, another is different. Okay, so two cases may arise in that scenario. Okay, if it is not uniform. So shear in beam of varying depth. Okay, so first case will be the bending moment will increase numerically in the same direction in which the effective depth increase. So for example, if you take this cantilever beam and there is a load applied at the outermost position, okay, outermost point, so the bending moment will increase in this direction, right? It will be P into L, as you can see, and in this case also the depth is also increasing in the same direction, okay. So in depth condition, what happens is the shear force V equal becomes VW minus M by D into 10 beta. So that is the formula, okay, where VW will be that the shear force due to this, okay, this P, okay, at the extreme fiber or any portion position. M will be the moment, okay, so M will be the moment that is generated at this at the section at which we need to calculate the shear force. This is the V, this V is the section at which we need to calculate the shear force, okay, anywhere, okay. So at that position, that section, the shear force that will be acting will be VW, which is this, minus M, that is the moment acting at that section because of this load, okay. So that is the thing. D will be the effective depth at that section. See, if this is the section at this section, what is the effective depth? And tan beta is the this value, this divided by this. So this ratio is the tan beta, okay. So using this you will get the shear force for that particular section, okay. So if the section is here, okay, so definitely because the depth is increasing, okay, so what is happens is depth is increasing at the direction the moment is increasing, so definitely the shear force at that section will be less as compared to this, okay. So the effect will be less. However, in the opposite case, when the moment decreasing moment direction, okay, is the same in which the effective depth increases, that means here the bending moment decreases this direction, but the effective depth increases this direction. Or you can say the condition in which the bending moment increases and the effective depth decreases, okay. So this is bending moment increasing, effective depth also increasing, both are increasing together same direction, and here bending moment increasing but effective depth decreasing, okay. So in that condition, when it is opposite, the V value will increase, okay. So it will be increase in it will be more than the actual shear force acting, actual load acting. Okay, so it will be V equal to VW plus M by D into 10 beta, where VW will be this value, M will be the moment at this section where we need to calculate the shear force, D will also be the effective depth here, 10 beta is this value. Okay, so it is logical. Okay, it is explanatory because the shear force was acting here. Okay, and plus it is also taking additional load due to the increase in depth. Okay, so definitely this shear force will be higher. Okay, this will be definitely higher. So that is self-explanatory also. Okay, so here it will be lesser because it is more than this, so it can take more, so it is less shear force. However, here it is lesser than this depth, so it will be more. Okay, so more will be the shear force that is acting. Okay, so that is the logic. There is also logical understanding. It can be self-explained. Okay, from the sketches. So these two are the criteria for varying depth. Okay, so one, it will, if the both the directions are same, it will decrease shear force, and if the both the directions are different, okay, opposite, so then the shear force will increase. Okay, so now let us try to fully understand this idea. Okay, so the shear force, okay, at varying depth. So for this, let us solve this problem. Okay, so a tapered cantilever beam, okay, of 2.5 meter span, okay, has a width of 300 mm. Okay, so width is this in this direction, so width is 300 mm, span is 2.5 meter, and it tapers from 200 millimeter depth at the free end to 450 millimeter depth at the support. Okay, so this is 200 and this is 450 Determine the nominal shear stress at a section 2.2 meter. Okay, 2.2 meter from the free end. So at this section, we need to find out the nominal shear stress. Okay, so the formula, because the moment is increasing this direction, depth is also increasing this direction, so it will be, here the shear force will be lesser than 50. Okay, so what will be the formula? It will be V equal to VW minus M by D into 10 beta. Okay, so this is the sketch. Okay, this is the line sketch of the problem. So 50 kilonewton here, 200 and 450 mm is the depth at these two locations. 2500 mm is the length of the section, length of the beam, and we need to find the shear stress at our distance to 2200 mm from the free end. Okay, so as you can see, V is 50 kilonewton. Okay, M is 15 to 2.2 at this portion, which will be 110 kilonewton meter. Maximum it is 125 kilonewton meter. Okay, and effective depth at this location, it will be 420 minus 25 minus 25 by 2. Okay, so here we have assumed the clear cover is 25 mm. Okay, and the phi, okay, so the phi value is also taken, I think, as 25. Okay, so diameter of the longitudinal reverse has been also taken as 25. So 420 minus 25 by 2, it will become 382.5 millimeter. Okay, and 10 beta will be how much? It will be this one, this value. So it will be 450 minus 200 divided by 2500. Okay, so 450 minus 200 divided by 2500, which becomes 0.1. Okay, so what will be the value? Value will be 50 minus 110 into 0.1 by 0.3825, right? Yeah, everything is meter and kilonewton. So the bending moment increases numerically in the same direction as the depth of the section increases, right? So the V value will be 21.242 kilonewton. Solving. So the design shear force V will be 1.5 into 21.242, which is 31.863 kilonewton. Okay. So the design, because it is partial safety factor of 1.5 is taken. Okay. So we overestimate on this. So it will be 31.863 kilonewton. Okay, so which is lesser than like 21 was itself lesser than 50, and also like 31, even after multiplying by 1.5, still it is lesser than 50, so it is less. Okay, so because both are moment and depth, both are increasing at the same direction. Okay, so yeah, so the nominal shear stress tau V will be V by BD, which is 31.863 into 10 cube by 300 into 382.5, which is 0.2776 Newton per mm square. Okay, so yeah, so that is the solution. So let us take one more problem. Okay, a series of beams placed at 3 meter centers, okay, are supported at masonry walls The slab thickness is 125 mm and ribs below the slab are 250 mm wide. The depth of the web is 250 mm. Provide tensile reinforcements and also designed for shear. Okay, so the width of masonry wall is taken as 250 mm. Distance between center to center of two walls is 5.5 meter. Assume 6 millimeter thick ceiling plaster and 30 mm thick floor finish. Okay, and take FCK value as 220 Newton per millimeter square, or the grade of M20. Right. So let us try to understand the problem in sketch. Okay, so these are the two walls, okay, which is having a distance of center to center distance of 5.5 meter here. Okay, above it we are placing a series of beams, okay, which are at a which are having a distance of 3 meters center to center. So we are placing beams here and it is having a distance of 3 meters center to center, if you see. Okay, so like from any portion to the same portion it is 3 meters. Okay, then above that we are placing a slab, okay, slab which is having a thickness of 125 mm and ribs below the slabs are 250 mm wide. So ribs are basically that is basically the beam itself. Okay, so that beam is having a width of 250. So or we can say the web. Okay, so it is having a width of 250. So if we consider that the slab and the beam is cast monolithically together, okay, so then we can say that the slab is having a thickness of 125 mm, the web is having a width of this one 250 mm, okay, and thickness of the web, okay, so the thickness of flange is 125, thickness of the web is 250. Okay, so thickness is the depth, okay, depth of the this slab is basically it will act as a flange. Okay, so the flange thickness is 125 mm, the depth the flange thickness is 125 mm, depth web's depth is 250 mm, and the width of web is 250 mm. Okay, so both are 250 250. So this is the beam. Okay, so this is 250 and this is also 250. Okay, so above this you have we have put a slab which is having a thickness of 125 mm, that is the depth of flange. Okay, we will consider that. Okay, so this is basically what it can be taken as. Okay, so this is a T section or a flange section. Okay, so this is 125 mm, this is 250 mm, and this is also 250 mm. Okay, so now let us start. Okay, so let us yeah, so as we know the specific weight of RCC is 25 kilonewton per meter cube, and the specific weight of plain concrete is 24 kilonewton per meter cube. Okay, or and specific weight is also known as unit weight, right? So the dead load, basically there will be three cases. Okay, one will be the 125 mm thick slab. Okay, one will be the 6 millimeter thick ceiling. Okay, and one will be the 30 millimeter thick floor. Okay, so here basically we are considering the dead load for the beam. Okay, we are only considering for the slab. Okay, because that is negligible, okay, as compared to the this one, the slab. Okay, so what is happening is, yeah, so if you see the dead load, okay, so it will become 25 for slab it will be 0.125 into 25, which is 3.125 kilonewton per meter square. For the ceiling plaster it will be 0.006 into 24, which will be 0.144 kilonewton per meter square, and for 30 mm thick floor finish it will be 0.03 into 24, which will be equal to 0.72 kilonewton per meter square, right? So adding all these three, we get the dead load to be 3.989 kilonewton per meter square. Okay, and let us assume the live load is 4 kilonewton per meter square. So the dead load has been found to be 3.989 kilonewton per meter square, and the live load is 4. Okay, 4 kilonewton per meter square. So that is basically the so we are considering the this one the load. Okay, so we are considering the load for the beam also. So I'm sorry, so we have considered, but in a the second, okay, so this in the second part we have considered. The first part we have considered the dead load for slab, ceiling and floor, which came to be 3.989. Okay, so adding this with the beam, okay, beam dead load. So what happens is, yeah, so the this one if you see here the beam dead load, yeah, so this is the beam dead load. So beam will be how much? It will be 25 into 0.25 into 0.25, because width of rim and the width of web and the depth of web. Okay, so both is 250 mm. So it will be 0.25 into 0.25 into 25, and we have taken here 5% extra. Okay, so this 5% is for 5% extra is because you take into account all these extensions. Okay, so these extensions are there because it will never be center to center, it will be little bit more. So we have taken 5% extra. So 5% extra is 1.05 into 0.25 into 0.25 into 25. Okay, so which is 1.640625 kilonewton per meter. Okay, so this is the rib depth. Okay, so that is basically the depth of wave only. Okay, so that's why we are assuming it as 250 mm itself. And this one, this was a dead load of slab. Okay, so that was per unit area. Okay, kilonewton per meter square. But if you see here, the distance is 3 meter, right, center to center, or between this center to this center. So if we take assume this as a T. Okay, if we assume this as a T section. Okay, so what we can say is, for one section we can say that this value, the dead load for slab. Okay, so that will be 3.989 into 3. Okay, for one part. Okay, because the center to center distance will be 3 meter, so every 3 meter there will be one part. Okay, so for one part it will be how much dead load for slab will be 3.989 into 3, which is 11.967. Okay, so for one beam and the slab, the equivalent slab portion. Okay, so we multiply the dead load of slab into 3, and that 3.989 into 3, it is 11.967, and the beam, okay, it is 1.64 0625. Okay, so for one particular piece. Okay, one particular piece of beam and slab equivalent. Okay, so that total comes to be 13.607625 kilonewton meter. Okay, so these two. Okay, so these two, it comes to, total it comes to be 13.607 625 kilonewton meter. Okay, so that is the dead load. Now the live load. Okay, so the live load, because we have considered this as 3 meter, so let us multiply this with also 3. So this total live load will be 4 into 3. Okay, so which is 12 kilonewton per meter. Okay, so for a unit part. Okay, so for a unit part, the dead load will be 13.6. Okay, and live load will be 2 at 12. Okay, so WDL is 13.607625 kilonewton per meter, and WLL is 12 kilonewton per meter. Okay, so now let us find the effective width and depth. Okay, so the effective width of basically the this one, the flange. Okay, so because that portion we don't know, so this, what is the effective width of flange, we don't know. Okay, so we will have to calculate this as we discussed last class, as you can see here. So for T beam, the effective width of flange is L naught by 6 plus BW plus 6DF. Okay, so L naught is basically the center to center distance, or between two zero moment distance. So that is LE by 6. Okay, so effective length, so that is how much? 5.5 meter, right? So 5.5, that is the distance between these two walls. Okay, 5.5. So this is this one, 5.5 by 6 divided plus BW, which is 0.25, 250 mm, plus 6 into 125 mm. Okay, so it is 5.5 by 6 plus 0.25 plus 6 into 0.125, which becomes 1.9166 meter, that is 1.917 meter. And the center to center distance of beam is how much? It is 3 meter, right? And so and yeah, so these are the two. Okay, so the effective width will be the lesser of the two. Okay, so the minimum of 1.917 and 3 is 1.917. So the effective width of this one flange is 1917 millimeter, and overall depth is 250 plus 125, that is 375 millimeter. However, effective depth will be 375 minus clear cover of let us take 25, so it minus 25, and let us also assume 20 mm bar, so it will be minus 20 by 2. So 375 minus 25 minus 20 by 2 is 340 millimeter. Okay, so therefore we can now calculate the mu from concrete. Okay, So moment carrying capacity from the concrete section is 0.36 FCK XUD XU by D into 1 minus 0.416 X by D X into BF D square. So substituting the values, we will get X by D value as 0.095. Okay, so that implies the depth of neutral axis will be 32.3 millimeter. Okay, so that will be less than the depth of flange, right? So it will be uh, less than depth of flange, which is 125 millimeter, right? So it is less. So because this one because it is less, so that means we can simply design like we can simply design it like a singly reinforced section, right? So simply reinforced section we can design. So the steel that has to be provided, okay, so the steel that basically needs to be provided is it will be equal to mu by 0.87 fy into d minus 0.42x. Okay, so mu value is how much? So yeah, so mu value is 145 point this one 23 into 10 to the power 6. Okay, so we have calculated it somewhere, forgot where. So yeah, somewhere we have calculated, I forgot. So the moment value is 145.23, okay, kilonewton meter. And the this one fy value is 415, okay. And this is yeah, so this is minus 0.42 into 32.3, right? So this is 1232, okay, millimeter square, okay. And so therefore this is the amount of steel, okay. So this is the amount of steel that has to be required, okay. So let us, if we provide 420 diameter bars, because we have assumed the diameter of bars to be 20, okay. So providing 420 bars, the AST provided will be 1256 millimeter square, okay. So now the steel percentage will be 1256 by 250 into 340, okay, into 100, which is 1.47%. And this formula is used for finding the minimum steel, okay. So it is 0.85 fy into 100, okay. So fy is 415, so it will be 0.85 into 100 by 415, which is 0.205%, okay. So as this value is greater than zero point 0.2, so it is okay, okay. So the shear reinforcement, now let us check. So VU is equal to 105.63 kilonewton. So the percentage of tensile reinforcement is 1.47%, right? And maximum shear stress for M20 as per IS 456 is 2.8 megapascal. And gamma V will be this 105.63, right? So this value divided by BD, okay. So 105.63. So yeah, so 105.63 divided by into 10 cube by 250 into 340. So gamma V will be 1.2427 megapascal, okay. And from table 19 we will get gamma C value as 0.714, okay. So as this value is more, so we have to provide stirrups, okay. And this value is less than 2.8, so that means the beam will we don't need to redesign, it is okay, okay. So gamma v is greater than gamma c and gamma v is less than tau c max, okay. So shear due to concrete, it will be Vc, okay. So Vc is 0.714 into 250 into 340, which is 60,690 Newton, that is 60.69 kilonewton. And shear to be taken by steel Vs is Vu minus Vc, which is 105.63 minus 60.69, okay. So that will be 44.94 kilonewton, okay. So we have to design for this. So for this VOS equal to, we have to use this formula again. So putting the values, we will get ASB by SVS 0.366, and if we assume stirrups of two-legged 8 okay, bars, SV value will come to be 273 okay. So actual center to center distance will be minimum of 273, 255, and 300, which is 255, okay. So Rounding it off, we will provide 885 two-legged stirrups at 250 mm center to center. Okay, so this is how we will design. Okay, so 125, 250, 250, 4, 225, 85 two-legged at the rate 250 millimeter center to center. Okay, so this is how the design has to be done. Okay, so let us take one more example. Design of stirrups for nominal shear. So this is for nominal shear. Okay, so when we don't require, okay, but we have to design. Okay? So here B equal to 250 mm, D equal to 450 mm, longitudinal reinforcement 5 into 25, VU is 60 kilonewton, concrete is M20, steel Fe415. So clear cover is taken as 25 mm. Okay, so effective depth will be 450 minus 25 minus 20 by 2, that is 415 mm. AST is 1570 mm square, P is 1.513%, right? So gamma V will be 60 into 10 cube by 250 into 415, which is 0.578. Okay, and gamma C max is 2.8. So anyways, it is okay. The section is okay, and gamma C value is 0.722. Okay, so this is itself more than gamma V. So that means we don't actually need stirrups. Okay, but still we have to design for nominal shear. Okay, so as you can see, gamma V is less than gamma C, less than gamma C max. So only nominal shear reinforcement is provided. Okay, actually we don't need, but still we provide the minimum. So for that, this clause, as I told you initially, so gamma, this taken as formula, it's gamma V minus gamma C value is taken as zero point 0.4. Okay, although it will be negative here, but it is taken as zero point 0.4. So ASB by VSV is greater than equal to 0.4 by 0.87 FY. So substituting the values, we get ASB by SB is 0.276, and using 8 diameter 2-legged stirrups, we get ASB as 100 mm square. So SB is equal to 362 millimeter. So maximum spacing, the spacing will be minimum of 362, 311 and 300. So it will be 300. Okay, so the stirrups, let us provide 8 8 diameter 2-legged at the rate 300 center to millimeter center to center. Okay, so that will be the case. Okay, so okay, so with this we come to the end of this class today. So let us now get the lecture, sorry. So let us now solve few problems based on this. So one, the maximum, first question, the maximum spacing of shear reinforcement measured along the axis of the member shall not exceed SV equal to 0.87 into Fy into ASB into D by VUS, 0.75 D, where D is the effective depth of the beam, 300 mm. Okay, so or the minimum of A, B, and C. So which of the four is correct? So definitely the maximum shear reinforcement have to be the minimum of SV. Okay, 0.75 D and 300 mm, provided that reinforcement is shear reinforcement is vertical. Okay? Stirrups is vertical. If it is inclined, it will be D. Okay? So if it is assuming it is vertical, it will be the minimum of all the three. So D will be the correct option. So you can refer this lecture also for that finding the answer. So yeah, so as you can see, it is the fourth option. Okay, minimum of all the three. Second question, match the list 1 to list 2 with regard to the angle of inclination of the crack pattern in a simply supported concrete beam. List 1A, diagonal tension cracks near the supports. B, shear compression cracks in the compression zone of the beam. C, flexure shear cracks in between the supports and midspan. D, flexure cracks near the midspan due to bending alone. List 2, 145 to 90, 3, 45 to 90. Okay. So, which of the option is correct? Okay. So the crack pattern for a simply supported concrete beam follows this. Okay, so cracks will be vertical due to bending alone near at the or at the midspan of the beam. So near the midspan, okay, the cracks will be vertical due to only bending. So these are called as flexure cracks. Okay. However, near the, as I told you initially only, near the supports the cracks will be inclined. Okay, so we have, that's why during derivation we have taken 45-degree the beta value. So the cracks are inclined at an angle of 45-degree at the supports due to shear. So these are called diagonal tension cracks or shear cracks. Okay. And if the cracks occur in the compression zone due to shear, that also inclines at 45-degree. Okay. And in between the supports and midspan, the crack inclination, okay, it increases from 45 to 90. Okay, as we gradually go from the midspan to support. Okay, sorry, from support to midspan. Okay, so these are known as flexure and shear cracks. Okay, flexure shear cracks, because both of the cracks are present in this in this type of cracks. Okay, So if it is 45, near to 45 it will be shear. If it is near to 90 it will be flexure. So it will be both flexure shear cracks. So matching that, we can say that A will be this one. A will be 1. Okay, so A will be 1. So you can say C is the correct option. Okay? So A is 1. B shear compression cracks in the compression zone. So this will be 45 again. So B1. Flexure shear cracks in between the supports and midspan. So it will increase from 45 to 90 as we go from support to midspan. So 3. Okay, C is 3. And D flexure cracks near the midspan due to bending alone. So this is 90. So D is 2. So C is the correct option. Okay. So as you can see, C is the correct option. Third question, design shear strength of concrete tau C in a reinforced concrete beam is a function of which of the following? 1. Compressive strength of the concrete. 2. Percentage of shear reinforcement. 3. Percentage of the longitudinal reinforcement. Or 4. Yield strength of the steel. Okay. A 1 only, B 3 only, C 2 and 3, D 4 only. Okay. So if you see tau C, okay, so that is mainly a function of the this one. It is a function of the percentage of the longitudinal reinforcement. Okay, so that is a function of the percentage of the longitudinal reinforcement mainly. Okay, so as you can see, tau is C is dependent only on PT equal to ASD by BT into 100. Okay, so percentage of longitudinal reinforcement, that is B. Okay, third option. Actually, to be more appropriate, it is both compressive strength as well as percentage, because for a given grade of concrete this value will be different. Okay, so it should be 1 and 3 both, but because one option is not 1 and 3 both common option is not given, you can only go for 1 or 3. So out of grade and percentage, more important is the percentage. Okay, so the mostly it will change by percentage. So therefore, the third option will be correct. So like, yeah, third option will be correct. That is B, 3 only. Okay. So B will be the correct option. So as you can see, B is the correct option. Fourth question: a balanced reinforced concrete beam of M25 grade and 300 mm is having a factored limiting moment of 125 kilonewton meter. The grade of steel is of Fe415. The effective depth to nearest multiple of 10 of the section is A 450 mm, B 350 mm, C 300 mm, D 400 mm. Okay, so which is the correct option? So yeah, so what we have to find out, the D effective depth is D. So because this is limiting moment and this is Fe415, so we can use the formula mu equal to 0.138 FCK BT square, right? So mu limit is 125 into 10 to the power 6. uh, FCK is 25, B is 300, and D we have to find out, right? So yeah, so we can use this formula, and from using this we will get D is equal to 347.5 millimeter. So 347. So nearest multiple of 10 it will be 350. So B will be the correct option. So as you can see, B is the correct option. Fifth question: following are the details of a rectangular beam with its 300 mm, effective depth 600 mm, clear cover 25 mm, tensile reinforcement is provided by 525 mm dia bars. The design shear force is 200 kN. Concrete grade is M20, steel grade Fe415, and for M20 the maximum shear stress permitted is 2.8 megapascal, right? So also the for calculating the design shear strength of concrete, the values of tau c with respect to for M20 with respect to PT values are given as from the IS code. So which of the following statements are correct in regard to the shear design of the beam? Okay, so is tau c greater than tau v? Is tau v greater than tau c max? Is tau v is less than tau c less than tau c max? Or is tau c is less than tau v is less than tau c max? Okay, so let us see. So width is B 300 mm, effective depth D 600 mm, area of tensile reinforcement is 5 into pi by 4 into 25 square, right? So it is 2454.3 mm square. FCK value is 20 megapascal, Fy value is 415 megapascal. So PT value will be how much? AST is 2454.3 by 300 into 600 into 100, right? It is 1.36%. And as per the values given here, or also you can take the IS 456, the tau c value will be for 1.36, 0.67 plus 1.36 minus 1.25 by 1.5 minus 1.25 into 0.72 minus 0.67. So that is basically the interpolation. So it comes to be 0.69 megapascal. Okay, and nominal shear stress, it will be VU value is 200, right? 200 into 10 cube by 300 into 600, that is 1.11 megapascal. So tau V is greater than tau C, okay? And tau max value is how much? Tau C max value is 2.8, right? So 2.8 is even greater than 1.11. So yeah, tau C value is 2.8, so it is greater than 1.11. So tau C is less than tau V is less than tau C max, okay? So yeah, so this D option will be the correct option. So statement D is correct option. So as you can see, it is the correct option. Sixth question. Following are the details of a rectangular beam with 300 mm, effective depth 600 mm, clear cover 25 mm, tensile reinforcement 525 mm bars, design shear force 200 kN. So basically the same only. M20 steel grade Fe415. For M20 grade of concrete, maximum shear stress is 2.8 megapascal, right? And these are the tau C values with respect to PT value for M20 grade, okay? So here, as per limit state, the critical shear capacity of beam is how much? So we have been asked to find the critical shear capacity, right? So the critical shear capacity of the beam, okay? So basically tau C, the tau C from the it will be VC, sorry. So it will be calculated from tau C. So it will be VC equal to tau C into BD, okay? So tau C value we calculated to be how much? It was around 0.69, right? So VC will be 0.69 into 300 into 600. So as you can see, 0.69 into 300 into 600. So we will calculate all the parameters as per the last question, and just multiply with 300 and 600. It will be 124.2 kilonewton. So that is the C option. So C is the correct option. So as you can see, C is the correct option. Seventh question. So, following are the details of a rectangular beam with 300 mm, overall depth 600 mm, clear cover 25 mm, tensile reinforcement 520 mm bars, design shear force 350 kN, concrete grade M20, steel grade Fe415, maximum shear stress for M20 2.8, and these are the tau C values for PT, different PT. So these are the statements. Nominal shear stress of beam is 2.06 megapascal. Shear reinforcement need not be provided. Beam has to be redesigned. So which of the statements are incorrect? Okay. So let us see. So width is 300. Effective depth is how much? 600 minus 25 minus 20 by 2, 565 mm. Area of tensile reinforcement 5 into pi by 420 square, 1570.8 mm square. FCK is 20 megapascal. FY is 415 megapascal. And yeah, so PT value will be 1570.8 by 300 into 565 into 100, which is 0.93%, and tau C value will be 0.603 megapascal, okay? So nominal stress tau V will be VU by BD. So VU value is 350, right? 350 into 10 cube by 300 into 565. Okay. So that comes to be 2.06 megapascal. Okay. So tau C value is how much? Tau C is 0.603. Tau V is 2.06 and tau C max is 2.8, right? So as you can see, this is the tau C is less than tau V is less than tau C max, okay? So hence we have to provide shear reinforcement, and because it is less than tau C max, it does not need to be redesigned, okay? So one is correct because 2.06 megapascal is nominal shear stress, but shear reinforcement needs to be provided and the beam is okay, it does not need to be redesigned, okay? So 2 and 3, okay, so both are incorrect. So correct option is C, okay? C is the correct option. So as you can see, C is the correct option. Eighth question. Two rectangular beams B1 and B2 are of similar cross sections with a width of 300 mm and overall depth of 450 mm. They are provided with 20 mm dia Fe415 bars on the tension side with a clear cover of 25 mm. The beams are constructed with concrete grade having a tau C max 2.5 megapascal. For the reinforcement provided and the grade of concrete used, it may be assumed that the tau C equal to 0.8 megapascal. The design shear in beam B1 is 350 kN and in beam B2 is 450 kN. Consider the provisions of IS 456-2000. Which of the following is true? Nominal shear reinforcement is required for beam B1 and the shear reinforcement should be designed for 350 kN for beam B2. Shear reinforcement should be designed for 250 kN for beam B1 and the section for beam B2 should be revised. Shear reinforcement should be designed for 250 kN for beam B1 and the shear reinforcement should be designed for 350 kN for beam B2, or the sections for both beam B1 and B2 should be revised, okay? So which is the correct option? So yeah, so let us see. So parameters B is 300 mm for both, right? effective depth D is 450 minus 25, okay, minus 20 by 2, okay, so it will be 415 mm. Tau C value is 0.8 megapascal for both, right? And uh, tau V, okay, tau V value will be different. So for this one beam one, it will be 350 into 10 cube by 300 into 415, which is 2.81 megapascal. And for B2, it will be 450 into 10 cube by 300 by 300 into 415. Okay, so this comes to be 2.81 megapascal, and this to be 3.61 megapascal. And tau C max will be Toxic max is how much? Yeah, 2.5 megapascal. So here, if you see, tau V is greater than tau C max. Okay, so maximum shear strength the beam can carry, even it is higher than that. The design shear stress is higher than the maximum shear capacity of beam. So that means it will fail in shear. Okay, so it will fail in shear. That's why the sections for both beam B1 and B2 have to be revised. So D is the correct option as per the analysis. Okay, so as you can see, D is the correct option. Ninth question: following are the details of a rectangular beam with 300 mm, effective depth 500 mm, clear cover 25 mm. Beam is carrying a factored UDL of 65 kilonewton per meter. Effective span of beam is 5 meter. The diameter of longitudinal bar is 20 mm. Spacing between the stirrups is 150 mm. Concrete grade M20, steel grade Fe415, and maximum shear stress permitted is 2.8 megapascal for M20. And these are the tau C values for M20 with different steel reinforcement. So consider the following statements in regard to the shear design of the beam. The beam section is an over-reinforced section. As longitudinal reinforcement, 5 numbers of 220 mm bars can be provided. The shear reinforcement will resist a shear of 7.5 kilonewton. The shear reinforcement will be met by providing two-legged 8 mm diameter stirrups at 260 mm center to center. So which of the following above statements is incorrect? Okay, these are incorrect. So factored load is 65 kilonewton per meter. Maximum bending moment acting on beam will be this one WL square by 8, right? So it is irrespective of whether it is your simply supported or fixed. Okay, it will be always maximum will be always WL square by 8. Okay, so it is 65 into L is the meter, 5 meter. So 65 into 5 square by 8, which is 203.13. Okay, and limiting moment of resistance of the section. So maximum this one maximum carrying capacity of the section will be M limit, right? So it will be 0.138 FCK BD square. FCK is 20, right? So B is 300, right? D is 500, right? So it becomes 207 kilonewton meter, which is greater than M max, which is 203.13. So because it is taken by concrete itself, right? So because it is greater, that means we can provide the tensile reinforcement lesser. Okay, so that means we can easily go for under reinforcement. Okay, because we always want the beam to first for fail in tension. Okay, so we can design it for under reinforced section. If this value would have been lesser than this, okay, if this value would have been lesser than this, then we could have gone for over reinforcement. Okay, or we could have gone for that is over reinforcement or doubly reinforcement. Okay, so because this value is more, okay, so that therefore we can go for this one under reinforced section. Okay, so we can provide less tensile steel so that it fails first. So therefore it is not an over reinforced section. Then area of steel required in this case. Okay, so we can use this equation. Okay, so this is a special equation where it uses FCK FY value for calculating MX and BD value also for calculating the steel required area. So it is zero point 0.5 FCK by Fy into 1 minus square root 1 minus 4.6 mx by FCK BD square into BD. So putting the values, we get the area to be 1394.96 millimeter square. So number of bar required will be, because we have been provided 20 mm bars, right? Yeah. So number of bars will be 1394.96 by pi by 4 into 20 square, which is 4.4. That is 5. Okay. So ST provided is 5 into 5 pi by 4 into 20 square, which is 1570.8 mm square. Okay. So yeah, so statement 2 is how much? 15708. Yeah, 520 mm bars. So it is correct. Okay. So factored shear force VU will be how much? WUL by 2. Okay. considering it is simply supported, so it will be 162.5 because we are going for maximum, right? That's why. So nominal shear stress tau v will be vu by bd, which is 1.08 megapascal. So PT value is 1.05%, and based on the tau c value 0.63, so it is less than tau v. Okay, and it is less than tau c max, which is 2.8. Okay, so we have to design for shear. Okay, shear reinforcement has to be provided. So still has to carry how much shear? 1.08 minus 0.63 into 300 into 500, that is 67.5 kilonewton. So shear reinforcement will resist a shear of 67.5 kilonewton. So it is true. And so let us assume two-legged stirrups of 18 mm dia. So ASB will be 100.5 mm square, and spacing will be 268.782 millimeter. So actual spacing will be minimum of 268.78, 375 and 300, which is 268.78, or we can go for 260. Okay? So we can provide two-legged 8 mm dia stirrups at 260 mm center to center. Okay. So the fourth is also correct. So only wrong is one. Okay. So which is incorrect? A, one only. So as you can see, A is the correct option. Okay. And last question, the rectangular width of beam 300 mm is having overall depth of 600 mm. The concrete grade is M20 and the grade of reinforcing steel is Fe415. Okay. The tensile reinforcement is provided by 520 mm dia bars. The clear cover is 25 mm. The design shear force is 500 kilonewton. The design shear strength of concrete tau c megapascal for M20 grade of concrete is given as 100 AST by BD tau C. Yeah, so these are the values for tau C with respect to tensile reinforcement for M20. So for M20 grade of concrete also, the maximum shear stress permitted is 2.8 megapascal. So which of the following statement is true? Provide two-legged stirrups of diameter 10 mm at the rate 100 mm center to center. Provide two-legged stirrups of diameter 10 mm at the rate 200 mm center to center. Provide two-legged stirrups of diameter 10 mm at the rate 300 mm center to center, or increase the depth of the beam. Okay, so which of the option is correct? So as you can see, FCK value is 20 megapascal. Okay, FY value is 415 megapascal. Okay, width is 300 mm. Okay, effective depth is 600 minus 25 minus 20 by 2, which is 400 565, right? Yeah. And AST value is how much? 5 into 5 pi by 420 square, which is 1570.8 mm square. So PT value will be 0.93%, and tau C value will be 0.603 megapascal. So yeah, critical shear capacity will be 102.208 kilonewton, and nominal shear stress tau V is VU, which is how much? 500 into 10 cube by BD, which is 300 into 565, which is 2.95 megapascal. But the tau C max value is 2.80 megapascal. So that is the maximum permitted shear stress. So it is the nominal shear stress is more than this. So the beam will fail in shear, and there is no use of providing any stirrups. Okay. So therefore we have to increase the depth. Okay, in order to decrease the nominal shear stress. So increasing this depth, it will decrease it below 2.8 megapascal. Okay. So therefore, we need to increase the depth of the beam. So which is the correct option? D. Okay. So as you can see, D is the correct option. So we need to increase the depth of the beam. Okay. So with this, we conclude the end of today's discussion. Okay. So yeah. So let us meet next week, Sunday. So and have a good week ahead. Okay, so best of luck. So with this, I would like to end today's discussion. Okay, thank you. Good night.